takes 1 day off. So before we start chapter 3, we have just one topic we didn't finish last time. So I will spend a few minutes to do that. Then we move on to chapter 3. So this is for RTO. We defined a estimator for the variance, which is SSE over n minus 1. And we try to prove it is unbiased, okay? Prove that the estimator is unbiased. So this is what it means by unbiased. The expectation of that equal to the true parameter. So we start from just writing out what is SSE. It's the summation of yi minus y hat. Y hat in the context of RTO, it is just beta 1 hat xi. This is y hat squared. And then we also know that beta 1 hat equal to summation of xi yi summation of xi squared. Okay. So first, we need to do some simplification of that before we use the e. So this is the summation of yi squared plus beta 1 hat squared summation xi squared. And this is where we stopped last time. So basically, you need to have negative 2 times beta 1 hat summation xi yi. But with this, we can figure out that the beta 1 hat summation x by x actually is beta 1 hat squared times summation xi squared. Okay, so this becomes the first term y squared minus beta 1 hat squared summation xi squared. Okay. Any question here? So basically, beta 1 hat multiplied by this equal to beta 1 hat squared multiplied by summation xi squared. Then you have plus 1 minus 2, you get minus 1. Okay? Okay, if there's no question, then we apply the E. You first look at what is the E of SSE. This is the E of, you take out summation, right? Summation E of yi squared minus, you cannot take out beta 1 hat squared out of E because it's also a random variable, right? But you could do summation of xi squared multiplied by E of beta 1 hat squared. Here you need to be clear which one is the random variable, which one is considered constant. So when you apply expectation, this is with respect to the distribution of the epsilon. The randomness comes from the epsilon, which is making y a random variable, but x is considered given constant. So you apply E or yi squared, and then you take out summation xi squared as a constant, then you apply E on the beta 1 hat squared. This is constant coefficient, okay? Don't apply E for x. X doesn't have randomness. All right. Then you have E of a random variable squared. We are going to use the variance to replace this. This is basically equal to the variance of yi plus E of yi squared. This is the yi squared within the E. So this is E yi, then you take squared. So that is E yi for each term, okay? Similarly, we apply the same trick for beta 1 hat. So basically minus summation xi squared multiplied by, this will be variance of beta 1 hat plus E of beta 1 not I, beta 1 hat squared, okay? Is this clear to everybody? Okay. Then you basically just plug in what is E yi, what is variance y. Variance y is just sigma, right? So you have summation of a sigma squared plus E yi is just a beta 1 xi squared. This is within the summation for the first term. minus summation xi squared multiplied by, what is variance of beta 1? It's just beta 1, right? Sorry, E of beta 1 is just beta 1. Variance beta 1 is sigma squared over summation xi squared. So this is sigma squared over summation xi squared variance plus E is just beta 1, okay, square. Now it's clear. Now you can see this summation xi squared cancelled. All right, so you basically have n times sigma squared minus sigma squared, so n minus 1 sigma squared. And this is beta 1 xi squared. How about this one? This is also beta 1 squared summation xi squared. Because this one, beta 1 is constant with respect to the summation, so you can take it out, right? So you basically get the summation of xi squared multiplied by beta 1 squared. So these two also cancel, okay? So this term and this term canceled. Now we just left with this. So basically, E of SSE divided by n minus 1 exactly give you sigma squared. It's done. Proof is done. So for RTO, it's relatively easier. If it's a simple linear regression, you just have more terms in here. You have a beta 0 hat term, but the process is the same. So in some steps, you have to basically expand the E of a random variable squared into the form variance plus the expectation squared. So that's all it takes. It's a little bit tedious. If you have more term, it just takes more lines. But the thought, the approach is the same. All right, any question for this part? Okay, then we can move on to chapter 3. So chapter 3 is just extension from what we learned from a single predictor to multiple predictor. So it's called MLR, stands for multiple linear regression. So the first step is to extend the data model from one predictor to multiple predictor. So this is your data model, y equal to beta 0 plus beta 1 x1 plus beta 2 x2 all the way beta p xp, where each of these represent a random variable. You have p predictors, x1 to xp. Each one represents different things. Remember, in the end, you also need to add epsilon. The epsilon is random noise. We still assume mean zero, common variance, sigma squared. So why we call it data model is because if you have collected xi, yi for n data points, then each yi is beta 0 plus beta 1, x1i, beta 2, x2i, beta p, xpi. You just need to add I to there, okay? So written in this kind of form is not very neat, so we can have a matrix form. So let's say we use a vector to represent y, y1 to yn. For the observation, x equal to a matrix. The first column is all 1 in order to represent the intercept. Then you have x11 all the way x1p. Basically, I index is index for the observation. It goes 1 to n. The second index, column index, is dimension 1 to p. Okay, so this will be x21, xn1. Then this will be xnp. Okay, this is x2p. Column index is dimension, row index is sample index. So with that, we can also write epsilon equal to epsilon 1 to epsilon n. However, all the epsilon I follow the IID distribution with n0 and sigma squared. And we write beta and beta hat as a p plus 1 dimension vector. Okay, so dimension is p plus 1 by 1. This notation shows it is a column vector. So basically, you can write your beta equal to beta 0, beta 1, all the way to beta p. Similarly, beta hat also equal to beta 0 hat, beta 1 hat, all the way to beta p hat. Okay, this is just our notation. So with that, we can represent the data model in matrix form. So the matrix form data model is y equal to x beta plus epsilon. The dimension of epsilon and y are the same. X beta, when you multiply x beta, because sometimes people write as beta times x. So you need to be aware of their dimension to make sure they are compatible in matrix multiplication. So this is dimension of x is n by p plus 1. Dimension of beta here is p plus 1 by 1. So you have to put x first, then beta. All right? And then when you do the regression, you regress the predicted value for y hat equal to just x beta hat. Okay? It's really neat, right? So this is just how you represent the regression problem. So next steps, we need to do least square estimation for the regression coefficient, estimate beta by beta hat, right? So the next step is least square estimate for beta. So how do you apply least square? Well, initially probably you are not comfortable with the matrix form because to do calculus over matrix is not that comfortable. The idea is the same. It's just the presentation is not comfortable. You may just give yourself a little time to first write it out in the scalar form. Let's say you try to minimize summation of yi minus y hat squared, right? So you can make your q, your objective function value, equal to summation of yi minus y hat squared. Plug in one step, so yi minus beta 0 hat, beta 1 hat, xi1, all the way to beta p hat, xip, this arrow squared. Then you can write the matrix form. So this is the summation of something squared is equal to the vector transform and multiply by itself. It's basically like the inner product between two vectors. So you can write as y minus x beta, beta hat, transpose multiply y minus x beta hat. Okay? So this is a scalar form. This is matrix form. So you can see here every part, summation of every element squared is equal to the vector transformed by itself. Okay? So this is a vector, column vector, transpose, get a row vector, and this is a column vector. Then you get a scalar. So Q is a scalar. So basically, in this context, once we introduce the matrix form, by default, we think all the vectors are column vectors. If you want to represent a row vector, you put transpose here. So when you see a vector with transpose, that basically means a row vector. So this is a row vector multiplied by a column vector. Okay, then you do partial Q, partial beta hat. A scalar with respect to a vector. So this is negative 2 x transpose x beta hat. So the way I wrote here, a scalar, if I don't put the transpose here, that basically means this is also a column vector. Okay, the representative here is a column vector. Okay, so how do I come up with this? So basically, a vector, row vector multiplied by a column vector, it's still in the squared form, quadratic form, right? Second order, then you take derivative, you still get, by using the same calculus, you still get the 2 times of something, Then you take with respect by the chain rule, you take a derivative with respect to the beta hat, you get x. But when you write down, make sure you end up with a column vector. Okay. So X is a matrix, X transform still matrix, Y minus this is a column vector. So this ensures that you result in column vector, okay? The dimension must match. Any question for this part? All right, okay. Now you basically set this equal to 0, it's a 0 column vector. Then you solve this, basically you have X transpose Y equal to X transpose X beta hat, okay? Then your goal here is to get the beta hat, right? In order to solve this equation to get the beta hat. So beta hat is just X transpose X inverse X transpose Y. So the reason we have to do X transpose X inverse Y instead of just directly X inverse Y is because the dimension of X may not be square, right? It may not be. If it's not square, you have to make it square by doing this. X transpose X make it square matrix, then you can do inverse. Okay? And some people may wonder, okay, what if it's not inversible? Right now, we don't assume any degradation on the rank. Assume it's a full rank, so you can do inverse. So if it becomes really bad, because outer X is data. If in the future you have like a coding arity between different columns, this one will be to do inverse over this matrix will be very bad. It will introduce large errors, and we will address that problem in the future, okay? So right now, just don't worry about that detail yet. Just assume we can do inverse on that, okay? Then you have y hat equal to x beta hat. Then you get x transpose x inverse x transpose y. Okay. So if you have no doubt over this part, so next we are going to define this matrix as H. So define H matrix equal to x transpose x inverse x transpose. As you can see, H only have x. There's no y. Then you can write your y hat equal to H y. So the matrix H, the reason we call it H is because it's a hat matrix. Why is a hat matrix? This hat, because it put a hat on Y. By multiplying by H, Y multiplied by H, it put a hat on itself. That's why we call H a hat matrix, okay? Some books may probably call this H matrix P because it's a projection matrix, right? A vector multiplied by a matrix is called projection. You basically project that to a plane. So that's also fine, but we prefer, in our class, I prefer to call it hat matrix. So whenever we mention hat matrix, you know it's a matrix that multiplied by y to make it turn into y hat. Okay. So next, we are going to look at what is the property of H. So there's a lot of interest to start with matrix H. Properties of matrix H. So first of all, H is symmetric, so H transpose equal to H. It is symmetric. Okay. How you can tell from here, if you do transpose, it end up with X. Then transpose the inverse, you basically get X transpose X inverse, then X transpose. That's exactly H. So H is symmetric. This is easy to prove. The second one, H multiplied by itself is still H. This is called idempotent. It's symmetric and idempotent. If H is symmetric and also idempotent, so basically X makes X transpose H is still equal to H, right? This is the result of the first two. right? All right, and also I minus h has the same property. So I minus h is also symmetric and also idempotent. Okay. So this is, you can easily prove that just by plugging in the definition. A little tedious, but you can easily prove that. So these are the properties we are going to use frequently in the future if we use matrix form. So next, I'm going to focus on the sum squares. So you have the sum squares for the simple linear regression. We know that SST equal to SSE plus SSR for simple linear regression. Does this hold for regression through origin, RTO? Does this one hold for RTO? No, no, okay, good. So the next question is, does this hold for multiple linear regression? What do you think? Does it hold for multiple linear regression? How about for multiple linear regression? Yes? Yeah, I think yes. So basically, the reason that makes it hold here is you still have the beta 0, right? The reason RTO no longer have this property because you get rid of beta 0. So it still hold for multiple linear regression, but we need to show it, okay? We need to show it. So SST start with the scalar form yi minus y bar squared. Then we eventually turn that into a matrix form. So this is the summation of yi squared 2 times y bar summation yi plus y bar squared and then summation, so you have n times y bar squared. Okay, y bar is constant with respect to the summation. Then you realize summation yi is n times y bar, so you have minus 2 n y bar squared plus 1. Minus 2 plus 1, you get summation yi squared minus n y bar squared. Okay, this is yi. All right. So one more step, this is the summation yi squared minus summation of yi, which will be n times y bar, right? Squared will be n squared y bar squared divided by n to give you this. All right. So in order to get the summation y squared, we know the summation of yi squared equal to just y transpose y, right? What is the summation of yi squared? These two things are different. Don't think that's equal. You easily get the first term. Summation y squared is y transpose y. What is summation yi then squared? So this one equal to y transpose multiplied by a matrix J, y, where J is all ones. Okay? J is a matrix that contains all one. So the dimension of J is n by n. Got it? J is n by n matrix because the dimension of y is n by 1, right? So J is n by n. It has all ones. So basically, you multiply by y transpose, you get a row vector. Each element is summation yi. Then you multiply by y again, you get a summation yi squared. All right. So with these two, we can write SST in the matrix form. So SST will be, the first term is y transpose y. Second term is y transpose jy. You can write y transpose I minus jy. oh, j divided by n. You have j divided by n. So summation yi squared is this. You divide by n here. This will be j divided by n. J divided by n. Okay. All right. So the SSE is in the matrix form. Then we can do the same for SSE and SSR. So SSE is summation yi minus yi hat squared, right? That's a scalar form. And written in the matrix form, this will be y minus y hat transpose y minus y hat. Right? Now you get y transpose y minus y hat transpose y minus y transpose y hat plus y hat transpose y hat. Then you have to use h to write y hat in the form of hy, right? So this is the first one is y transpose y. Then you realize, okay, these two actually are same by the property of h. Second and third term here cancelled. All right. So basically, y hat transpose is hy transpose is equal to y transpose h transpose, right? This will be hy. So h is one h, right? So basically, you get when you can get rid of one h, you basically can make the last one y or y hat makes no difference, right? So these two cancel. So minus y transpose y hat. Right, one more step, you have y transpose I minus, this is hy, so hy. Okay, question is around how these two terms cancel, right? All right, I will do that. So why is these two terms cancel? So you write y hat transpose y hat equal to hy transpose hy, okay? Then one more step, y transpose h transpose hy, right? Right? Then you have h hat h, this is symmetric, so it's hh, right? hh idempotent is h, so we get y transpose hy, right? Right? Agree? Yes, okay. You can also write y transpose h transpose y, right? Agree? Make sure you're happy with this. Yes, okay. Then this will be just hy transpose y, right? Okay, what is hy? It is y hat transpose y. All right? All right, okay. So these two cancel, so we have no problem with them canceling each other. All right, so we have SST, SSE. We still need to write SSR in the matrix form. So SSR is summation of yi hat minus y bar squares. So this is the summation of yi hat squares plus y bar squared n times, right? Minus 2 times y bar summation of yi hat. So the summation y hat equal to summation y, because the summation ei equal to 0 still holds for multi-ligand regression. That is, you get that from the, if you do like a partial q partial beta 0 hat, you'll get that. Okay. So I did the matrix form that include everything. I did the matrix form, but if you plug in each of the partial q partial beta 0 hat, you still have a summation of e equal to 0, summation ei equal to 0. So in that case, this is summation of yi hat equal to summation of yi. Okay, it equal to summation that's equal to n times y bar. So minus 2 y bar squared n plus 1 n y bar squared. So you get minus 1. So summation of y hat squared minus n times y bar squared. Okay. Any problem here? Oh, okay. Then next we are going to write that into the matrix form. So this is summation y hat squared. It is y hat transpose y hat. Okay. Minus n times y bar squared. We already have that when we handle SST. So minus n times y bar squared eventually becomes y transpose j n y. So y transpose matrix j n y. Just y, no bar. Okay. And for the y hat transpose y hat here, if you pick something from here, you know this is what? You just use the intermediate result from here. Y hat transpose y hat. This is y hat. So y transpose hy. So this is y transpose hy. We just did it here, right? Minus y transpose j n y. So you take out y transpose y on both sides, you get h minus j n y. So this is the final for SSR. This is final for SSE. This is final for SST. Are they equal? So I minus h plus h minus j over n equal to I minus j over n. Both sides are y transpose y, right? So SST equal to SSR plus SSE holds still for MLR. Now you proved it. All right. So what other property do we know about HX? So in addition to the two obvious ones, symmetric and idempotent, which you can easily prove just by a few lines here. The other important property here also include the summation of rows and columns that sum to 1. So each row or column of H sum to 1. Okay. So another property of H, any row or column sums to 1. So once we proved for row, it also proved for column because it's symmetric, right? Because it's symmetric, it's row sum to 1, column also sum to 1. All right, so how do we show this one? So how do we show this one? So answer one question. What is H-X multiplication? Given the definition of H is X transpose X inverse X transpose. This is H multiplied by X. What is that? It will be just X, right? Because X transpose X inverse X transpose X, they cancel. They become I, then you have I, X alone. So if Hx equal to X, what does that mean? No, it doesn't mean H equal to I. No, certainly not. Or if you consider H is projection matrix, you multiply by, you take any column from X, consider it's a vector, right? Once it is projected by H, it projects to itself.
So does that follow that H squared equals to H itself?
Of course, H squared equal to H.
Okay.
Here it has that property. So I'm showing that this is a definition for H. This is H multiplied by X equal to X. So if you take X is matrix, remember it has many columns. All the columns of X. The first column is all ones, right? Then you have all the predictors. You have P predictors. Each one represents a predictor variable. You have n data points. So if you take any vector from H, have H projected. Where did it project to? It projects to itself, right? On the other hand, remember, H is also a projection matrix. It's a projection matrix. It projects Y onto Y hat. Let's see the plane we try to project to is a plane spanned by all the columns of X. Let's see. For easy, I will just draw a 2D plane. If you take any vector, you have H projected. The image will be a vector in the plane spanned by the column of X. So let's say this is your Y. This will be projected into Y hat. Y hat written as, remember Y hat is written as X beta hat, right? It's a linear combination of X. It is a vector lying in a plane spanned by the vectors of X. So Y hat here is a vector lying in this plane. So what if you take a vector from the X matrix and have H to project it? What do you get? You get itself. So because the vector is already in this plane. In other words, if I take anything already from this plane, I have H to project it, it projects it to itself. Okay? So how does this property help us to prove any row sum to 1, any column sum to 1? How does that help? So let's say we could let U be a column of X matrix. Okay? I said this is a X matrix here. Take any column. Let's say we call it U. Then what is HU?
U.
Yes. Brilliant. Yes. Because if you take whole matrix, Hx equal to X. So if you take any column of X called U, it's still equal to this column. HU equal to U. So if the whole vector, HU is vector, right? U is vector. If the whole vector is equal, that basically means every element of the vector equal, right? So HU, the ith element, equal to U, the ith element. Okay. Still with me? Now, if U equal to the first column, the O1, then what do you see? What do you see? Sum of the ith row of H equal to 1, right? And this I apply to all the I for all I equal to 1 to n. All right? So the first is general. All right. This is the most general, hi equal to x for the whole matrix. Then you take column, any column, this still holds. And this still holds for every element for this vector. These are the general applied to any column. And then you make U equal to the first column, you'll get, actually HU will be just, HU for the ith position is just the sum of ith row of H. All right? So because H is also symmetric, X transpose equal to H, therefore, sum of the ith column of H also equal to 1. So written in a algebra form, so basically you have summation of Hij, summation of all I equal to I, for all j equal to 1 to n, summation of Hij, if you summation over all the j, that's a summation over all the j is a row sum, so equal to 1, for all the I equal to 1 to n. Okay, let's summarize this too. If you summation all the I, that means the column sum to 1. If you summation over all the j, that means rows sum to 1. All right. So with this property, can you explain why you wrote down U? Write down U is in order to get to the sum of a row or sum of column. Oh, you totally messed up the proving logic here. The purpose to write this is in order to get to what is the sum of H. When U is all ones, you get to the sum of a row for H. Okay? Of course, in this conclusion, it doesn't have to be all one, but you are using this specific case in order to get to the sum of a row H. All right, your purpose is to prove this property, the sum of a row, any row, equal to 1. All right. So with this property, we can also use this property to prove that the summation y hat equal to summation yi. Earlier, we didn't give you, but I said that by using the least square, if you do like partial q, partial beta 0 hat, you can get to sum of ei equal to 0. But here, using the property we just proved, that's just offer a alternative approach to prove that property. So you can use this to show that the summation of yi hat equal to summation yi. Just use the property I just showed here. Can you do that by yourself? Not really. Okay. All right. So maybe I will just write down one more step. So we know that y hat equal to hy, right? Starting from here. Then you write that as a element form. So you have y hat 1 all the way to y hat n. A vector equal to h is a square matrix. It needs to be actually same size. I draw it too small. So h is what's the dimension of h? Dimension of h should be same as row of x. That's n. Okay, so n by n. Y is y1 to yn. Okay. So h here is n by n. Remember. All right. So what is the summation of yi hat? That is summation of all the elements in the vector, right? So you may just write out what is the, leave the summation at the last step, the outer loop. Then you work on what is each yi hat. What is each yi hat? Each yi hat here is hi, let's say the ith row 1, y1 plus hi2, y2, all the way to hin, yn, right? Each of yi hat, that is the ith row here, equal to ith row here, right? Ith. Then you to take a summation, I goes 1 to n. The whole thing needs to be in the summation, right? Yes. Then you see here, for each summation, I goes 1 to n, you have specifically y1 here. It's not considered a variable with respect to I. So you basically can write out as y1 times summation hi1, I goes 1 to n, plus y2 times summation hi2, I goes 1 to n, right? Blah, blah, all the way to n. Agree? Then you basically have summation of any column equal to 1. This is summation hi1, I goes 1 to n. So the first column, second column, all the way to the nth column. Every column sum to 1. So you have y1 times 1 plus y2 times 1 plus yn times 1. Every y times 1. That is summation yi. Okay? Who asked this question? Summation equal doesn't mean each element equal. Summation y hat equal to summation yi doesn't mean every y hat equal to every yi. Okay? So if every yi hat equal to every yi for all I, certainly summation of yi hat equal to summation yi. Okay, but the converse is not true. You need to know the direction is from if to then, not from then to if. Okay, right. So the direction is from if to then, not from then to if, okay? So we proved this sum of y hat equal to sum of yi. That's equivalent to say summation of ei equal to 0, because ei is defined as difference between yi and y hat. And this is just the second approach to show that. And the first approach is by using least square partial q partial beta 0 hat, you will get this. What else? So we are in simple linear regression, the x bar, y bar, this point falls exactly on the regression line. In MLR, is this still true? Remember, in simple linear regression, x bar, y bar falls exactly on the regression line. Is this still true for multiple linear regression? Yeah, people made a gambled guess. Basically, it is true. Okay, so this is still true. So can you prove it? So in this case, your regression is no longer a line, it's a hyperplane. In simple linear regression with one predictor variable, it's a regression line. With multiple linear regression with px, with p predictor variable, you actually have a hyperplane. So basically it means x bar, y bar exactly falls on the hyperplane called y hat equal to beta 0 hat plus beta 1 hat x1 plus all the way beta p hat xp. It's a hyperplane, okay? So this one still falls on that. Why? Here you may remember, because its dimension is no longer 1, your x bar actually equal to x1 bar, x2 bar, xp bar. Okay, so here is a capital letter to represent the name variable, random variable, lowercase represents subsequent value. Sometimes I may not be very strictly following that. So here, you remember x bar here is no longer one value. It is a point in high dimensional space. Okay. So in order to prove that, you show that each of yi hat equal to beta 0 hat plus beta 1 hat xi1 plus all the way to beta p hat xip, right? Then you do a summation of yi hat equal to, when you do summation over this, you get n times beta 0 hat plus beta 1 hat summation xi1 all the way to beta p hat summation xip, right? So what is the summation? This summation, you write one more step, beta 0 hat plus beta 1 hat. What is summation of xi1? I goes 1 to n. It will be just n times
x bar,
x, yeah, n times x1 bar. Okay, beta p hat. Summation of xip will be n times xp bar. Okay. Then you divide by n to get y bar. Y bar is still summation of yi hat divided by n. What do you get? You get beta 0 hat plus beta 1 hat x1 bar all the way to beta p hat xp bar. Now you see here whether this x bar y bar falls on the hyperplane. You plug in the formula right here to check whether this satisfies this equation. You plug in y bar for y hat, plug in all the x bar, right? Because x bar is combination of all the x1 bar to xp bar. Plug in the x1 bar, xp bar to all the variable name x1 to xp. You find out x bar, y bar satisfy this equation, okay? So x bar, y bar satisfies this equation. This equation I highlighted here. Then it's proved x bar, y bar still on the hyperbola, all right? So all the property you have for simple linear regression can pass on to multiple linear regression, but you cannot pass them to regression through origin. Okay, so it's not a matter of how large is your dimension, it's whether you have the intercept. Multiple linear regression and simple linear regression both still have the beta 0, even though for multiple linear regression you have more predictors. All the properties we had earlier still true. And also in simple linear regression, because you only have one predictor variable, so you have summation of xi, ei equal to 0. How about in multiple linear regression? In multiple linear regression, you won't just have xi because x itself is a higher dimension, but you would say summation of xi for any dimension p, ei equal to 0. This p stands for all the p equal to 1 to, let's say, a capital letter P to represent the total dimension here, for all p equal to 1 to p. So you would be able to write out this xi for each particular predictor variable. Okay, this is still true. This is something you obtained by doing partial Q, partial beta P. Do the derivative with respect to the coefficient for one dimension, you get that. Okay, question? All right, so next thing is, since we already proved the sum squares, they are still equal, right? We proved that SST equal to SSE plus SSR. So next thing is I want to check whether the degree of freedom is still equal. Where is our sum of squares? Okay. So SST you still write as yi minus y bar squared and the sum. What is degree of freedom for SST now? For SST, okay, show this formula again. SST equal to this. What's the degree of freedom for SST now? N minus 1, yes. Now we are talking. The formula is the same. So each yi bring in 1 degree freedom. So summation yi give you n degree freedom. But you calculate y bar as summation yi divided by n, you lose 1 degree freedom. So it is n minus 1. What is the degree of freedom for SSE? Where is my SSE? Here. This is SSE. This is the formula you need to look at. So yi is 1 degree freedom for summation yi is n, right? How many constraints did you use in order to calculate yi hat? Y hat is combination of beta 0 hat, beta 1 hat, all the way to beta p hat. How many constraints are there when you calculate y hat? P plus 1. So basically, you have P plus 1 constraints, you have n degree freedom. What's the resulting degree freedom? Yes, exactly. So n minus p minus 1. That's the degree freedom for SIC. Now, just by looking at, just to make the left-hand side equal to right-hand side, you can easily figure out this is P, right? But you need to know why it is P. Why is it the degree freedom for SSR equal to P? Why does that hold? So the formula for SSR is here. You have y hat minus y bar. What's the degree freedom here? Y hat. When you calculate y hat, you don't have n degree freedom because you have a hat here. This is not a independently disputed like yi, okay? Yi, each observation is independent of other, so you have n degree. But this is y hat. Each y hat is calculated by using the formula beta 0 hat, beta 1 hat, all the way to beta p hat, okay? So you have p plus 1, 3 pieces in y hat. You use one constraint in order to calculate the y bar. Y bar is summation y divided by n. So it's p plus 1 minus 1 constraint. So you get p, okay? So this degree freedom p for SSR is also for the regression line. In this case, it won't be a line, it's a hyperplane. It's also the degree freedom for the hyperplane. It has coefficient beta 1 to beta p, also an intercept, that's p plus 1 parameters controlling that. However, there's one constraint. It must pass through x bar, y bar. It loses 1 degree freedom. So either way, no matter how you look at it, it's p. All right? Any questions so far? All right, no question then. The content from this lecture is from section 3.2, section 3.4. 3.1, introduction, doesn't really have much material. 3.3 is a example. I think 3.5 is also some explanation. We don't need to go through that, but the content coming from here. And also, in addition to the content from the book, I also added a lot I think is useful. So my lecture note is not a subset of the book. And then the same hold for the other way around. The book is also not a subset of my lecture note. So for this part, I basically didn't follow the order the material is organized in the book. So basically use my lecture note as your standard. Okay? All right. So next time we are going to touch the bigger topic of the unbiased estimator, blah, blah, blah. This kind of thing I'll leave to next time, okay? So today I plan to stop here. All right, so before you leave, I will ask a polling question.